Let S is equal to 1, 2, 3, 4 be the set of non-zero residue classes modulo 5. Show that S is a group under multiplication modulo 5, where binary operation is defined as if A, B belong to S, then A dot B is equal to R, where R is the remainder obtained after dividing the usual product AB of A and B by 5. Now coming towards its solution. Since S has finite elements, so we will construct Cayley's table, and binary operation is of multiplication, so we will construct Cayley's table with respect to multiplication. Now let's construct the Cayley's table. In the top left corner, we will write the binary operation, that is multiplication in this case, and in first row and first column we will write all the elements of S, that are 1, 2, 3 and 4. Similarly 1, 2, 3 and 4. Since it is given that modulus is 5, so after multiplication, if we get an answer equal to or greater than 5, then we will divide it with 5 and write the remainder as the answer. Firstly, we will multiply 1 by all of these elements one by one. 1 multiplied by 1 is equal to 1, 1 multiplied by 2 is equal to 2, 1 multiplied by 3 is equal to 3, 1 multiplied by 4 is equal to 4. Now we will multiply 2 by all of these elements one by one. 2 multiplied by 1 is 2, 2 multiplied by 2 is 4, 2 multiplied by 3 is 6, which is greater than modulus 5. So we will divide it with 5. 5 times 1 is 5. Here we get remainder 1. So here we will write 1. 2 multiplied by 4 is equal to 8, which is greater than modulus 5. So we will divide 8 with 5. 5 times 1 is 5. Here remainder is 3. So we will write the remainder here, that is 3. Now we will multiply 3 by all of these elements one by one. 3 multiplied by 1 is 3. 3 multiplied by 2 is 6, which is greater than modulo 5. So we will divide 6 by 5. 5 times 1 is 5. Remainder is 1. Here we will write the remainder, that is 1. 3 times 3 is 9, which is greater than modulo 5. So we will divide 9 by 5. 5 times 1 is 5. Remainder is 4. So here we will write the remainder, that is 4. 3 times 4 is 12, which is greater than 5. So we will divide 12 by 5. 5 times 2 is 10. Here remainder is 2. So we will write the remainder here, that is 2. Now we will multiply 4 by all of these elements one by one. 4 multiplied by 4 is 4. 4 multiplied by 2 is 8, which is greater than 5. So we will divide 8 by 5. 5 times 1 is 5 and we get remainder 3. So here we will write the remainder, that is 3. 4 multiplied by 3 is equal to 12, which is greater than 5. So we will divide 12 by 5. we get 5 times 2 is 10, remainder is 2. So here we will write the remainder, that is 2. 4 multiplied by 4 is equal to 16, which is greater than 5. So we will divide 16 by 5. 5 times 3 is 15. Here remainder is 1. So we will write the remainder here, that is 1. Since the Cayley's table has been constructed, so now we will check the axioms of group one by one. First axiom is closure law. Since all the answers in Cayley's table are elements of S, which means closure law is satisfied. Or we can write multiplication modulo 5 is closed over S, that is A B product belong to S for all A B belong to S. Since first axiom is satisfied, so now we will check the second axiom, that is associative law. Multiplication is associative in residue classes modulo, which means that multiplication modulo 5 is associative over S, that is A multiplied by B multiplied by C is equal to A multiplied by B multiplied by C for all A, B, C belong to S. So second axiom of group is also satisfied. In third axiom of group, we have to show the existence of identity element. 1 is identity element under binary operation multiplication. We can clearly see that 1 belongs to S, which implies that 1 is the identity element in S. Since identity element exists, which means that third axiom of group has also been satisfied. Fourth axiom is existence of inverses. When we apply binary operation on two elements of a set and get identity element, then those two elements are inverses of each other. When we multiply 1 by 1, we get the identity element, that is 1, which means that inverse of 1 is 1. When we multiply 2 by 3, we get the identity element 1, which means that inverse of 2 is 3. And when we multiply 3 by 2, we get the identity element 1, which means that inverse of 3 is 2. And when we multiply 4 by 4, we get the identity element 1, which means that inverse of 4 is 4, which implies that inverse of each element of S exists. Which means that fourth axiom of group has also been satisfied. Since all the four axioms of group are satisfied, hence S under the binary operation multiplication is a group, which is required proof.